Probability distributions also have an expected value, which is a mean and a standard deviation, and they're calculated in a particular way. I don't necessarily need you to know these formulas. They're here for reference if you would ever have to do this by hand. We're going to use technology, and the Excel file for this one is called Discrete Probability Distributions, and it does these calculations for us. Now, the mean, this formula here, just want to talk about it a little bit. It takes each of the x values, the random variable values, and then multiplies by the probability of that x value. And then that sigma here is the sum of all of those products. So I want to show you just this example. It's more for reference. I don't want to go through it but in detail, but it gives us a probability distribution. It's number of pencils brought to class. So 0 is paired with 15%, 1 is with 63%, and so on. If you're calculating the mean, you're taking this 0 times the 15%, then adding next row 1 times the 63%, then the next row 2 times 20%, and then the last one 3 times 2%. It's that formula there. When you do that, it gives you your mean, which is 1.09. It's like the average number of pencils that people bring. Now, the variance is a lot more complicated here, and you can look at the formula. It does use this 1.09 here. This is that mu that we just calculated. But it's more complicated, and we're just going to let technology do this calculation for us. Yeah. Okay, so the technology is the discrete probability distribution, and I want to show you that one on our course. Excel files and discrete probability distributions. I'm going to download that one. And open that up. Make it a little bit bigger. Okay, so here, x is this column here. Probability of the x is the second column. You want to put these probabilities in decimal form. So for the example that we just had there, 0, 1, 2, 3 for x, and then 0.15, 0.63, 0.2, and 0.02. You can see here it calculates it pretty quickly. 1.09 standard deviation is here. Also that 0.4219 calculates those things very quickly for us. Okay, so pull this back up, and this next part is looking at games of chance, and hopefully we'll demonstrate how these games of chance can be manipulated so that the house wins. Sometimes it's pretty obvious, sometimes it's not quite as obvious, but when we calculate this expected value, it gives us an idea of what would happen in the long run. and we can use that to make predictions of how much we would win or how much we would lose. So you're playing a game where you roll a six-sided die, you roll the die once, and if it's odd, you win $1. If it's even, you lose $2. And then what's the expected value of this game? Now, whenever we're losing something, if we're taking that perspective, we would use negative numbers for that return. If we're earning it, we use a positive number. Now, just looking at this game of chance, it doesn't seem fair, right? $1 versus $2, odd or even, are the same chances, but we would lose more than we would gain. So this one is not fair. We can see that with the expected value. And I'm going to write this down. So the return value, rolling an odd, we would win $1. Rolling an even, we would lose $2, so -2. Probability of both of these is 0.5. They're even. And if we want the expected value, we could use technology. I just want to show you. It's pretty quick when you have only 2 rows. So it's 1 times 0.5 plus -2 times 0.5. That's just 0.5 minus 1, which gives us -0.5. Because it's negative, in the long run, we'd expect to lose money. Now we can go further with this. Suppose that we played this game let's say 500 times. You can say we'd expect to lose and we do this the -0.5, and just write that to -0.5 there, times 500 is -250. We'd expect to lose $250. So we can use that expected value to make predictions of things in the long run. It gives, of course, an approximate value, and with random chance, it won't always be exactly that value, but it will get close to that value. Okay, so here's another example. This one's harder to tell if we would lose or win at first. And it says, consider a bag of marbles, 12 purple marbles, 28 orange marbles, and 1 gold marble. You decide to play a game where you select a marble and you follow these rules. Gold, you would win 50. Purple, you would lose 50 cents. And then orange, you would lose a whole $1. If you play this game once, what's the expected value of your winnings or losings, and what does this mean? So I'm going to set up a table and just put event and then put return and probability. And here, the event is a gold marble, a purple one, or an orange one. And the return for this one is 50. We would lose 50 cents for the purple one, and we would lose a full $1 for the orange one. there's a total of 41 marbles. You add those together, gives us 41. So the probability for this one is 1 out of 41. Probability for the purple one is 12 out of 41. And the probability for the orange ones is 28 out of 41. Okay, so here we have our table. And we can get our expected value using Excel. So I want to show you that to show you how to do the division with the numbers. So typing 50, negative 0.5, negative 1. Gotta get rid of that one. And then for 1 out of 41, I'm going to put the equal sign, put 1 / 41. That does division 1 divided by 41. If you want to do 12 divided by 41 equals 12 / 41. Then the last one equals 28 / 41. Press enter. And that's it. So here's the whole distribution placed into the file. And it gives us an expected value of 39 cents, 0.39. Okay, so if we go back to the notes, our expected value is 39 cents, which is positive, which means in the long run, we'd earn money. Yeah. So this would actually be a game if someone offered you to play it 1,000 times, you would want to agree to play this game. You'd likely end up earning money. Okay, now games of chance can also be manipulated by controlling the prices so that in the long run the house wins. And it does require a little bit of algebra in order to do this. But it's kind of cool to see how you can control these things and make things profitable if you were running a game of chance. So it says you need to set up a roulette wheel for an upcoming festival. You create a wheel with 10 wedges. You decide 2 wedges are designated prize wedges. The other wedges result in no prize. And if the prize costs $20, how much should you charge each spinner to make an average of 50 cents per spin? Okay, so I'm going to write down a table again. Put events, and then return, and probability. And there are 2 events that could occur. Either the person wins the prize. Let me put spinner wins the prize, or the spinner wins no prize. Okay, so if the spinner wins the prize, we're losing $20, but we're also gaining how much we're charging for each spin. So let me just write here, since we don't know something, we'll take the algebra approach of defining it as a variable, and we'll say let x be how much we charge. That's for one spin. Okay, so we would get how much we would charge for them to spin, but then we would lose $20 in giving them the prize that they won. If the spinner wins no prize, we get how much we charge them. We don't lose anything other than time. So those are the two returns that we have here. Now, the probability, we have two wedges that are prize wedges, so 2 out of 10 are prize wedges, so I'll put 0.2 here. And the rest of them, using the complement rule 1, minus 8 out of 10 are no prize, which gives us a probability of 0.8. Okay, now the expected value. We can calculate, and since it's algebraic, we have to actually write this down. X minus 20, multiply that by 0.2, plus x times 0.8. And we're going to set this expected value equal to what we want to earn per spin, which in this case is 50 cents. We want the expected value to be 50 cents. Now I got to remember our algebra. I distribute this out. That gives me 0.2x minus 4 plus 0.8x. That's still equal to 0.5. Combine the 0.2 and the 0.8 gives us just x. Then minus 4 equals 0.5. We add 4 to both sides. And we get x equals 4.5. So we should charge say at least $4.50. It's kind of an awkward price, so you need quarters for that. Maybe just bump it up to $5. Then you would be earning $1, about $1 per spin. Okay, so they can be manipulated, and those games of chance where it's really random that you either win or lose, they're always in favor of the house, especially in a casino. There are things that are like skill games, like you can be really good at poker, which does involve probabilities, but there are some skill games at casinos, but like the slots, anything that's like truly random, are always going to be in favor of the house. Okay, now there's notation for probabilities, and these are going to be good for you to know for calculations. The ones that are kind of weird are the less than or equal to. They have other phrases that are used as well. At most R, no more than R. Greater than or equal to is also the kind of weird one. At least R, no less than R. Those are all the same ways to say that the same thing. yeah, so just make sure you are aware of those. You can reference these for the homework, but just make sure you know them. Okay, so here the notation is a little bit strange, so I wanted to go through this. The probability distribution is giving us the number of dentist visits, which is designated as x, and then the probability of those x's given here. We can answer questions. This one's looking for the probability that x equals 1. That's really just a lookup. It's 36%. This one right here. Look at where 1 is. It's paired with 36%. Now, this one is strange. It's saying 2 is less than or equal to x, which is less than or equal to 3. That's just two numbers, which are 2 and 3. And we add those two together. So taking the 40 here for a probability of 2 plus 14% probability of 3, that gives us 54% for the overall probability. Okay, now for probability x is greater than 1. Greater than 1 doesn't include 1, so it's the 2, 3, and 4 plus. Those three there. We add those three together. And that gives us 58%. Okay, last one. X is less than or equal to 3, so that includes 3, and then everything else that's less than it. All of those there. We could also get this by the complement rule. If we do 100% minus this 4% gives us 96%, or you could add them all together. Either way, it gives you 96% as the probability.